So, thank you very much to be here. I also thank the organizer to invite me. It's a great honor to present reflections about work, some part of the work of René Thom. So I had the chance to discuss of him part of them, and he was it's preferable. I try to speak in English. My English is very bad, but some of the transparent are in French because when copying Thom, I have not translated him. And Thom was very interested by information theory and very critical with the today's status of information theory, mainly issued from statistics, especially statistical mechanics, the work of Boltzmann, that he considers today as really the proof of non-understanding by scientific community of, for example, phase transition. And so there is a very good document, chosen by Michel Porte, or citation, where you have many about information. So I start only with two of them, then I will shift to the books of Thom. So I don't know if I try to translate or no? No, okay, I read them. Toute information est d'abord une forme. Et la signification d'un message est une relation de caractère topologique entre la forme du message et les formes caractéristiques du récepteur, c'est-à-dire les formes susceptibles de provoquer une excitation du récepteur. Réduire l'information à sa mesure scalaire, évaluer en bits, c'est réduire la forme à sa complexité topologique, c'est pratiquement tout oublier de son caractère signifiant. En fait, c'est d'une certaine façon, parler d'information comme on le fait, to speak information as we do today, is to forget that it is a transmission of form. J'essaie de montrer, donc c'est la dernière partie, c'est que, donc, qui est très relié à ce que Madame vient de dire ici, de montrer dans quelle direction pourrait se constituer une véritable théorie de l'information qui, à mi-chemin entre sémantique et sémiologie, véritable thermodynamique des formes, s'efforcerait de revenir à une analyse proprement morphologique des formes de messages. Donc là, il y a quelque chose de plus d'une certaine façon. Enfin, c'est déjà présent dans la première, c'est que il y a en quelque sorte there is two use of forms. There is a form either in reality or produced by the model, but there is also another thing which it is that message have forms necessarily and imply forms. They could be related, but not necessarily confounded with them. And in this book, the first one, information appears a lot. In the second one, when I will speak about Esquisse of Sémiophysique, in fact, the term of information appears less, but Thom's practice now his own information theory, in fact, in the book after this one. So here you think a lot of questioning about information. Même si l'usage actuel du vocable est abusif et injustifié, il n'en reste pas moins que le mot recouvre une notion utile et légitime. That is, for Thom, it's important to develop information theory. Alors se pose le problème de donner un contenu scientifique à la notion d'information et de la dégager de la gangue stochastique où elle se trouve emprisonnée jusqu'à présent. La thèse générale de ce chapitre, donc c'est celui sur la dynamique des formes, chapitre 7, et que là où, en général, on parle d'information, on devrait user du mot forme. La mesure scalaire d'information doit pouvoir s'interpréter géométriquement comme complexité topologique d'une forme. Malheureusement, il est difficile, dans l'état actuel de la topologie, de donner une définition précise de la complexité d'une forme. C'est quelque chose, en tout cas, something that will be useful to really formalize, understand information and communication of information. So I will comment two suggestions of Thom. There is a lot of suggestions. The main one is after that, is the same as in the preceding talk, in some sense, is to use the semantic model given by accident of creoles, and that's the whole picture of catastrophe theory. But Thom also tried to understand what could be really a significative exchange of information. Okay. And he says, so it has something to do with forms. So I read the sentence. Entre deux systèmes présentant de la récurrence, donc essentially he discusses not only static forms, but dynamical systems. Okay. L'exemple est celui de deux rotations sur des cercles. Donc ça, c'est moi qui décris. Il y a toujours apparition de résonances dont la stabilité est d'autant mieux marquée que le rapport des résonances a un petit dénominateur, d'où un échange de signification. Donc en fait, c'est donc la première suggestion de Thom. Vous imaginez donc deux systèmes dynamiques très simples, puisque les deux consistent donc à tourner. Par exemple, ça peut être donné par des difféomorphismes du cercle, avec donc des rotations différentes. Et maintenant, vous les couplez, et vous avez un système dynamique sur le tore. Donc, a priori, et ce système, si on prend le produit des deux dynamiques, est très instable. Donc, ce que dit Thom, c'est que, en fait, tout voisin de ça est dépendant, effectivement, du rapport oméga 2 sur oméga 1, ici. Vous avez des systèmes qui, eux, deviennent stables, parce que ils sont faits, donc dans ce cas du tore, avec donc des courbes ici, curves on the torus, which are attractors and repellers. And more, so you have a stable dynamic. So this is now. But it needs a deformation that is near the product, not exactly the product. And you find all this picture that was studied, for example, by Arnold and people that for and Alain Chanciner also, of the possibility. Here you have the rational number. And you have domain of stability, which has more larger with small small denominators. Okay? And he says this form here is, in some sense, the form of exchange of information. Okay? So information here is given by a dynamical system, but it signifies a real interaction between both. You have no interaction when you take the usual product. So this is one of the images we must have in our head, because all the other images I will present will consider systems, and important property, perhaps the main important property, are what happens when you consider composition of them, and when you consider eventually projection onto subsystems. Okay? So this is a kind of dynamic of interaction of several systems, okay? And it is essentially governed by something which is central in the work of Thom, which is a universal unfolding. When you couple different systems, you will see here a picture which describes their possible interaction. Of course, it puts this picture also specialized on the bifurcation of each individual system. Okay. So it is a kind of construction from several systems. And the second remark of Thom, I think very stimulating, is can be followed in this direction. Okay. He tried to understand if, because he recognized also that the usual notion of information by statistics is efficient. Okay. So it's not nothing, even if it is a way to non-understand, it's not nothing. So, lorsqu'un événement de probabilité P se trouve réalisé, notre information se trouve augmentée de la quantité moins K log P. Donc ça, so this is a very ancient remark that Thom doesn't see it, but it is the origin, the first time that people measure information. Okay. He says it's a good quantity which explains somewhat well what we understand by information is the logarithm of this probability, and it measures, in a sense, the knowledge we acquire after the measurement. Then Shannon, of course inspired by Boltzmann and Gibbs, define his own measure of information. In fact, information is a bit more complex. I will show the formula after perhaps, but here it is the entropy. So it is the basis to construct every information. After the experiment, it measures what we could gain after all possible experiments as new knowledge. And so you take the entropy as the mean, sigma p, of this quantity, J log p. Alors, I skip, that is my sentence. We would have to consider the whole story to go from here. And notably Kolmogorov, which already known that a better notion is complexity, but as Thom said before, we don't know really what it is, except in some special case, and Kolmogorov knows well what it is in the case of algorithm. And he would decide, he wanted that, to start from a notion of information, well-founded, to deduce probability. Now, Thom say, okay, this is usual information, but it is a trace of a geometrical operation. So we make a hypothesis that the event that is measured by the probability correspond to a submanifold with a singular point in a smooth manifold. So I will divide this here. I replace this submanifold, in a sense, with singularity, isolated singularity, with singularity of function. And you know, you have this picture of unfolding here, that you have a potential, like x4, for example, which is here. And except that this potential measures the event, and this event here is very degenerate, in a sense. So he has codimension 2. And this event, which are less degenerate, you know, well, this picture has codimension 1 in the space of unfolding. Then you say that, in general, so Thom considered two cars which will meet in a point along two roads, and the event is when they meet. So you can modelize with something like that. And he introduced a size of this of the event, and here it is kind of event which is here on the stratus. And he say that if the codimension is the number m, okay, then the logarithm of the volume, okay, which is m log epsilon, is this measure of information, okay, from probabilistic point of view. Okay. That this is a measure of the event when you consider that they are not punctual. So it's important to get this kind of augmentation, okay, by neighborhood. Okay. But geometrically, in fact, this number, okay, is something which is really the geometry of the singularity, okay, because it counts what are named the vanishing cycle, okay, of the singularity. Okay. And this is a measure of topological complexity of this theory. In fact, so Milnor considered singularity of functions, okay, f of z1, zn, okay, equals 0, for example, singular in one point. Okay. And when you see, when you consider the level, okay, 0, okay, it has a form, okay, but this form, okay, is what happens near the singularity. And near the singularity, you are over C, okay, to make this theory of vanishing cycle. I just want to give you the idea and why it interests so René Thom. Yeah. And it's over C. And in fact, if you take every fiber f equal u for number u near 0, you find smooth manifold. It's a function of isolated singularity. But this smooth manifold now has really a form. Okay. And this form, okay, is measured by this homology, okay, which is here, for example, the one of torus with point. Okay. And so this can be, this has a large, in fact, extension, okay, this behavior. And Thom contribution, the main Thom contribution here, okay, was to consider the case of maps, okay, going from Rm, or including Cm, okay, to Rp, okay, including Cp, okay, for every M, every P. Okay. And to ask if, can we, suppose you have a singular behavior over a point here, okay, can you describe how the singularities, okay, by such a picture, okay, the deformation, okay, which transforms it in a disparition of true form. Okay. So it's really in the spirit of what he expects, okay, for information, that is to translate a dynamical system, okay, into combination and dynamics, okay, of understandable forms. Okay. But here, in some sense, they are the simplest possible form, okay, because they are given by spheres. Okay. So you have a round spheres, in that sense. Donc Bernard knows very well how they can be round, okay, when you deform simple singularity. And Thom found a condition, okay, which is named condition A, on this map, okay, which complete the Whitney condition, say W, okay, and which imply, according to much more recent work, okay, like perhaps it is Ledung-Tran, the first one, and then Claude Sabar, okay, which shows that with such condition on the map, okay, which say in some sense they are not too dangerous. Well, it is a condition that Thom was very interested by this condition of unblowing, okay, in this. And you can guarantee in some sense a description. It's of course more complicated because you have to restrict to the different strata to understand, but you still have vanishing cycle. So there is a problem for Thom, in some sense, especially in respect to information, which is hidden here. Okay? It is this description works very well on C, but what is the byproduct over R? Okay? For example, here it's a non-trivial question, even for surface. Okay? The surface case, this is only a dimension 2 singular object. Okay? How many real cycle disappear? Okay? Something which is visible on this kind of picture of real functions. Okay? But still, it is more difficult. I don't want to speak about that. But it is to give this example, okay, which could be developed a bit more, but not too much. Okay? For Thom, could be the root of a geometric interpretation of information, even the probabilistic one. So it could be, you could be, if you understand correctly things, okay, you don't want to suppress the statistical physics, okay, but only to include it in a more understandable theory. Okay. Because he knows, of course, that the traditional theory of Landau, for example, for phase transition, okay, is not sufficient to explain the experimental data. And so here it's il ne faudrait pas croire. Alors, so this is what happened here, in some sense, is also that immediately you have multidimensional objects. Okay? You have many singularity, and you have manifolds, okay, of higher dimension. Okay? And so he addressed the problem, okay, of what is a semantic model in general, okay, because it seems too much restricted to linear structure as a syntactic language. Il ne faudrait pas croire qu'une structure linéaire soit une nécessité pour transporter ou stocker l'information, plus exactement la signification, donc on voit bien qu'est-ce qu'il veut dire par information. Bien que l'idée ne nous en soit pas familière, il n'est pas impossible qu'un langage, un modèle sémantique dont les éléments seraient des formes topologiques ne puisse présenter, du point de vue de la déduction, des avantages sérieux sur le langage linéaire que nous pratiquons. En effet, les formes topologiques se prêtent, par produit topologique, composition, etc., à une combinatoire infiniment plus riche que la simple juxtaposition de deux séquences linéaires. Donc il envisage vraiment, voilà, de pouvoir utiliser ces modèles mathématiques, ceux-là, de bifurcation de forme, comme langage, et même peut-être directement en accédant au niveau sémantique, c'est-à-dire au-delà, hein, donc de l'expression, donc la linguistique de la théorie. Donc le modèle sémantique par excellence, selon Thom, ça c'est moi, donc je peux le dire en anglais, so the semantic model by excellence, according to Thom, corresponds to a multidimensional language, and it is a system of creation, dispersion of chaos, okay, as we just saw, okay, of metabolic or generalized catastrophe. Okay. Donc these figures support the sense. So it's remarkable because, so in the question I have mentioned Middle Age philosophy, but in fact there is a very nice correspondence between some part of this book of Deleuze, which interroge of logique du sens, okay, at the same year of model mathematique of Morphogénèse, okay, which reminds that in a sense, what is central, okay, is semantic, okay, are not the words, but it is the events, okay, as everywhere in Thom. Okay, it's not the object, okay, it is relation in time, or for example, the verbs, okay, are events, okay, and they are situated in the theory. So Deleuze interprets the Stoicism, but the Stoics were not very far from it in the element we know of their linguistic theory, where you have some kind of this frontier between inside the mind and the world, the outer world, okay, between statements, proposition, and inside, okay, and the reality. And in this frontier, what happens, okay, is really singularity. Okay, that is what makes the sense, in the sense, is the presence of singularity. Okay. And so this is the central assertion of this work of Deleuze, okay, which interprets the stoicist as Thom interpreted Aristotle later. And this opens to this second part of the work of Thom, of semantic, which itself he named a new depart. Okay? And we have seen the coverture in English, but this is in French. This one, Esquisse. In this new volume, in the sense, as was said just before, things are presented in the reverse order. Okay? In some sense, first ontology and the philosophical notions, okay, like pregnance and science, okay, which are made to express the sense. Okay. Then the language, then biology and techniques, which are intimately related in the model of Thom. Okay. And then, after that, at the end, an essay to formalize the Aristotelian physics. Because in the first book, in some sense, you started with physical notion, okay, to end with philosophy through biology and language. Okay. And there are pictures, okay, which goes in this book. Okay. This is strangely, Thom says that in this work there is no mathematics in the usual sense. Okay. And even he tried to see if there is some conjecture, okay. And he find one, a conjecture. Okay. We say that generic paths, okay, in a space of configuration, okay, encounter only simple accident, okay? And it's very important, I think, for his semantic. Okay? And this simple accident are this one, that is the birth of the this one, the end. Okay, and of course you can have a true birth, okay? And the end. So these four drawing, okay, in some sense, compose anything. Okay? Which could be understood along a path. Okay. Of course, you need whole stratification to generate this accident. Okay. And this is also the origin apparatus. It is Wildigen. No, I forgot the letter, which will speak here also, and which present this composition of the pictures. Okay. Given by intersecting now the strata of the discriminant in the unfolding, okay, which are locally given by this picture. But you also have a very interesting path, okay, that Thom follows all along the book. Okay. He starts, okay, with the fold. Okay. So I represent like that. And then he immediately considers that, in sense, associated, okay, to this picture, there is something much more interesting, okay, which is a dynamical cycle. Okay. And he named hysteresis. That is what Thom's wants to use in everybody in the book, okay, in the fact that, in some sense, when you have a fold, okay, it is a sign of a totally new dynamic, okay, which generates cycle and which could be understood by cycle. Okay. And the proof of that, say François, that in fact he continues, and what is the main figure of this book, in a sense, is this one, okay, here, which means that you have here a concatenation of poles. That you see as a concatenation of cycle. Okay. And this is here that comes this condition of Argemy, and in a sense all the book use preceding catastrophe theory in a totally new context, okay, as was said, the context of intelligibility in general, to produce these pictures, okay, for explaining the plan of animals. Okay. So the central result in biology, and also the imagination of humans. Okay. That is how they construct a tool. And in fact, the starting of this discussion, this passage here, is about will, water will models. Okay. So this condition that traditional, so investigation of living entities, okay, has a great, large common part, okay, with invention, technical invention in human society, and of course, this technical invention are also present in other animals, okay, not only humans. Okay. And now I shift, so we will recover Thom at some moment, but I want to show that already in science in general, okay, and in new development that I will modestly present about information in a very special case, okay, we find elements asked by Thom. Okay. Is, not, of course, it's not true that today information is used in a different way than before. For example, if you read the model of semantic communication in machine learning, okay, what you will see as definition, okay, is something which exploits Shannon only, through some monsters, like, for example, the probability of everything in the world, okay, which is the function, the first function used, okay, to construct semantic. So it is not very serious, but still people can compute with that, and so it happens. Alors, in psychology, because in psychology, you will see several, I say, true information spaces, okay, in the sense of Thom. Okay. So there are similarities with what asked Thom and also departures. Okay. For instance, perceptual cognitive universal as reflection on the world. This is a very imaginative psychologist, Shepard, okay, which is known to have studied the displacement of solid, okay, and the time, okay, you recognize that two solids are identical, okay, and it shows persuasively that this is proportional almost to the time that you need to make the transformation, to realize the displacement. And he considered many geometrical spaces, mainly metric, okay, and associated to every sensory modality. So one of the best known, okay, is very ancient. Okay? It is the space of color. Okay? The space of color, so I say 3D, I wrote 4D, but it is in fact 3D. Okay? It is 3D, but it has an action, okay, of affine. Okay? So here you have the standard. Here in general you have black and white. Okay? Here you have the circle of int, of u, so around it. Okay? And for example, the usual light, okay, is represented by a Gaussian around the point, okay, as something round, okay, in the standard representation. And why I find that's because if you deform the light, okay, you can consider this deformation of the sphere. It gives you an ellipsoid, okay, and it explains, okay, your perception of colors, okay, and how you will correct from inside, okay, the activity of the neurons, okay, to keep information. Okay? Because it is very important for information because, in a sense, this representation of the color space okay, present the main problem. What is the main problem from the point of view of information seems to be to identify objects. Okay? That is to attribute a color to an object, which is totally non-trivial because if you illuminate this object by different kind of colors, it changes its perceived color. Okay? So all the work here is to separate okay, the light and the reflectance okay, of the object, which is really the problem of reconstructing useful information about the world. Okay. And this picture, which was anticipated by a psychologist in the 19th century, in fact, is now much more connected to brain activity. It is measured in some areas of the brain okay, that neurons really works with respect to this space. Okay. So their activity is measured by point in the space, and when you change the illuminant, they change according to the model. Okay. For example, there is a guy, which is named Webster, which shows that. Oh, but there is a much more fundamental example, okay, which is the space around us, okay, what it is. Okay. That is a question that first physicists say it is a gift of God. Okay. That is, it was the answer of Newton as soon as the question was asked, okay, because before that it was not really asked. But now it's not evident because we work with model of space-time okay, with our 10 dimension. Okay, so why it has this dimension and why this structure? And it was a problem examined by Poincaré, okay, which tried to understand if given sensory data, you can recover the space around us. Okay. And this is a kind of theory of information that I have no time to explore. But in both these cases, what is apparent okay, is that this case of information okay, are of homological nature. And for Poincaré, it's because he will describe different kind of sequence of sensation okay, and try to establish deformation from one sequence to another okay, and define not the space. He was not able to do that. It was very sad, in fact, to not recover the space. But he recovers the space of movement in the space, which is not nothing, by this procedure. And Grassmann, Pluquer, many mathematicians, okay, at the time they invented linear algebra, in fact applied linear algebra to define the space of color exactly by this way, that to compare linear combination of colors, okay, and to understand that with 3 colors it's sufficient okay, to satisfy almost everybody. And this is the kind of homology. But of course, at this time we don't know. We have no mathematical theory of what is the space okay, or the category of space okay, from which this is the true homology. Amazingly, this is a transition with what follows. With a neurophysiologist, Pierre Baudot, we discovered that Shannon information, in a sense, is also of homological nature. And in this case, it's really possible to describe the space from which it is an homology, but it belongs to a category with generalized usual topological space, which are made by Topos, okay, invented by Grothendieck. Okay. Of course, it will not have satisfied Thom, because in his book, he says that, of course, la gangue stochastique, okay, donc justement interdit de comprendre, forbids to understand Shannon information geometrically, but he also says that he does not recommend at all in the same book to read, no, in the second book, perhaps in Esquisse, to learn something about category. So certainly it's not a good answer. It is not in the text, but it is in the in notes about on the chapter where he presents precisely a category, okay, which is for the plants of animal, okay, and to where go a pregnancy. Okay. And so he used absolutely the language of category and limits, okay, but he wants unco-limits in a sense. But he said, no, stop. It's not necessary to study probability, to study category theory. And yes, it is this slide. So I will not give all the details, okay? But it starts with trying to find topological invariant, okay, of networks made by random variables. Okay. And these networks, okay, form a category when you use marginals, okay, as a morphism. Okay. And you can define also conditioning, okay, by the variable. Okay. And you look at probability like variable coefficients, okay, for this system. Okay. And now we can interpret the fundamental, this is named fundamental information, equation of information, okay, of Shannon, okay, which says that you can construct an action, okay, of the variable on the function of probability through this formula. Okay, that is, you take the mean of the conditioned function. Okay. And this is exactly what you need, okay, abstractly to define the homology theory. And in fact, the computations were made differently first, but we were surprised that applying the standard theory, we found that Shannon entropy this is a universal class. Okay. And in fact, it is a unique universal class in this framework. Okay. So it was a bit surprising, but in some sense, Shannon was very aware, okay, that this equation, okay, and the functional equation satisfied by his quantity, that is entropy and also the mutual information, I will show, is certainly important, even if it don't use a lot, because the main result of Shannon are asymptotic. Okay, that is, he tried to understand what are typical message, okay, in very long succession of message, okay, under some hypothesis, okay, like ergodicity, for example. Okay. So what is central, and I don't know to answer to that, is the relation, okay, between the asymptotic theory, which justify all the application of information, Shannon information, and this foundation, okay, which is, this is in some sense the only topological invariant possible. Okay. So this is the closest possible answer today to this question to interpret geometrically. So certainly it will be much better. It is possible to embed a lot of standard finite dimensional probability inside unfoldings. Okay? Because if you look, for example, at this simple one, the interpretation, okay, here of what happened for potential, okay, along such a path, okay, is really a probability. And it's related to a very deep tool here, which is named the period map, because this period map is exactly what we want to connect the vanishing cycle to the unfolding. Okay. And so this probability is given by integrating a differential form. So it's not impossible that, in some sense, this homological result here could be the trace, okay, the sign of something deeper involving unfolding to transform the standard Shannon theory into something more geometric. And so more recently, with Jean-Claude Belfiore in Huawei, France, in Paris, okay, in fact, we were motivated by what it's possible to, with a neural network, or deep neural network, this artificial neural network, okay, or what are the obstructions, okay, to do something about sense. Okay. To do this machine, even if it cannot move and something, so you have many objections, philosophical, very interesting objection, okay, that it cannot understand what has a sense and what has not sense. For example, it's easy to show that GPT today have no idea of what is the sense of signification, okay, but still it works. And so the goal is to try to understand at least the obstruction. Okay. And so we want to define purely semantic information. And here the path was to start with this result in homology and to construct the analog, okay, in a well-established semantic framework. So here the semantic framework is very standard and limited. We take as language a traditional, what is named type theory, but I don't want to enter the details. Okay. And the semantic is given when you represent this language in a category. Okay. And more concretely in a topos, because you have to represent sub-object, you have to represent final object and so on. Okay. So it's much better to work with Grothendieck topos. And here, well, in some sense, we have analog tools with what you use in probability. Because what are the variables? It is natural in this very simple context to take usual proposition, the sentences, okay, which you in the language expressed in the category. And what can replace probability are a system of axioms. Okay, that is the theories. Okay, it plays the role of what is known about the validity or not of the proposition. Okay. And it happens that in this context, you automatically have a good notion of conditioning. So I will not enter, because it's really here that category theory enter, because it's given by an adjoint, secondary adjoint functor. So I don't enter, but still you have a very good notion of conditioning by a proposition, to condition a theory by a proposition. Therefore, we can opt to have an information, okay, by looking at the homology. The problem is that the homology is trivial. But in fact, it happens also for the same reason in quantum probability. That if you do the same thing as classical in quantum, you don't get non-trivial homology class, but you get a whole apparatus, okay, which are given by complexes of vector space, okay, named Bar complex, which plays the role of a kind of homotopical algebra related to the problem. It was considered like that by people in the last 20 years. Okay. So we will use that, okay, to construct something topological. So I will accelerate. So I just say that when computing, you see that in fact we find that every for people which know homology construction, every cocycle is a core boundary, but it is the same as in quantum. Okay? So we have tried And if we look at numbers, in fact, we don't find something very interesting. So we were inspired here by a seminal work in the context of semantic information made by Carnap and Bar-Hillel, which explain well why it's legitimate not to look at ordinary classes, but classes with value in set. And here we take not only set, but topological space. So we try to replace the quantities, like entropy, for example, by a space, or information by a space. And it's possible to translate, to transport the first steps of the tools for this homotopical algebra in the case of space. And Carnap and Bar-Hillel, in fact, stopped very early, and they come to statistical entropy. So it was not really very used. And here I show what are the definition of this entropy, starting with something which will replace the fundamental entropy in quantum statistics, and which is made by assuming that spaces are embedded. Okay? When, for example, you take a theory which is implied by another, so the theory is weaker, so its space of information is embedded. Okay? And so we translate all the usual axioms by things where you have no operation plus or minus from standard algebra, but only things coming from topology. So that's why we choose the category of CW complex, because here all these operations are well defined. And so you find, for example, the definition of information at the end, but it's not the most important. I want to show you the application of a very simple language. And the simplest language was considered by Carnap and Bar-Hillel. It is made by having a collection of subject or object and a connection of attributes. Okay? And in general, this attribute take a finite number of value. Here we take only 2. Okay? So this gives a very simple language of first order, okay, with our sorts. Okay, what the things very simple, but still it permits to express a lot of data in practice. Okay? So that's why it is used in informatics. And so the simplest one is this one, for example, toy language. You see, you have only 3 subjects, A, B, C, and you say if they are old or young, or male or female. So you see, but the sentences could be very complex, okay? Because the whole complexity here is the OR operation. For example, if I say E is a male, young, B is a female, or C is a young male, or A is an old woman, you begin to have sentences that nobody can understand. Okay? And so what we expected from the information spaces, in this case, if they exist, okay, is that you see if a sentence has a meaning or if it is far to be understood. And it is what happened. And from where comes this information? They all come from the use of the symmetry group of the language. So what is, in some sense, the basis here of the whole information theory is the fact that you have a symmetry group. Okay? It's the same in quantum, where you use a unitary group to construct everything. And so here you see, for example, the first information space. This information space concerns the class of orbitons of the group, and they are given, in this case, by groupoids. Okay? I skip totally the construction here because I have no time, and it is a bit cumbersome. But the thing is that we can construct. It is not evident at all, even for the language L23, But there is a paper now ended, except some picture, which shows that we can construct this whole collection of space naturally under the group G for this language. Okay. So, and this is the theorem that there exists this extension of information theory. In some sense, it doesn't extend the whole algebra underlying homology. It extends the first steps where we can express algebraic operation by geometrical operation. And here I see it could be applied not only to using the group theory, but it could be applied when you use an order on the variable, as we do in classification. Okay. So what is important is here. This is the result in some sense. What means this information? And we had the chance that Shepard, the same Shepard, in fact, worked on a problem which when he tried to discriminate if people, when there are rules to construct something, do people learn what is constructed by heart, or do they use the hidden structure? And what is spectacular is that these people do not know at all the hidden structure, and they are unable to describe. Yeah. But still, they use this structure, and the problem was to identify a collection of. So it is with four objects, okay, with 3 attributes. And you take list of 4 objects, okay, with different attributes, and you ask to the subject to recognize. You show randomly, and you ask to recognize. And the result is very spectacular. Is that here it is on the right. Okay, it is that the difficulty to learn. To recognize if this is a good presented series of objects, okay, only depends on the rules, which are hidden. Okay. And it gives an order, okay, so on the orbit of the group. Okay. And people than 61, okay, have proposed different models, okay, for that. And we have shown that, in fact, our semantic space are able to answer. And so this is the formula on the top. Because you have a relative entropy, you consider the classification, okay, relative to its rules. Okay. And by chance, in this case, the space is very simple. Okay? It is made essentially by an union of a certain number of projective space. So you just have to count the space. And in this case, when we count, okay, we recover exactly the order. But not only that. Okay. In fact, we recover the order after that subject discover after a lot of experiment, okay? And except for the simplest one. And if we take into account not only the symmetries to compute information, but the other tool, which is given by these trees, okay? This is ordering the. You look first if it is red or if it is a square or something like that. Okay? Here you see the whole picture, that is also the progression of the subject. Okay? And in fact, what is important for us, that is every known measure of purely logical complexity or other measure of information we have proposed, okay? Either of statistical origin or of algebraic origin, are able to do that. Okay? It was expected that, in fact, it is pure logic. Because there are roles, more complicated are the roles, right? More difficult will be the task. In fact, it's not true. It is not like that. And really, it is something much more subtle, okay, which links the information concept, okay, to the roles, okay, which allow to make the ranking of the subject. So, in some sense, we have an interpretation of the first quantity. We are trying to find. So I have no time to. So I finish with that. I'll finish now. It is time. Okay. I have a collaborator from Huawei Paris, which are working with networks. Okay, and I could show after somebody interesting. We could reproduce this experiment with artificial network. Okay, and still we see that the artificial network can learn and distinguish the rules, but at this moment it is not human. That is because the tests were also done with many animals, okay, including monkeys, and they have their order, which is not the one of human, that using apparently a more elaborate semantic, and our network badly, sometimes they, except, of course, if you inject the origin in group theory. If you do that, the network becomes even better than human. Okay. So I stop just by this connecting again with this cycles. Okay. Here, what could replace in general this group in this simple language? Okay. For example, any notion, okay, that a network or us can manipulate, okay, seems to be related to the structures that Thom and Wilgen have used, okay, also, and which is original or comes from catastrophe theory. So I stop. Thank you.
A very naive question about the topos you use. What is the logic? Is it the standard logic or is it sophisticated logic associated to this topos?
In here, the topos is standard in this case, because for the language, okay, it is just the topos of representation of the symmetries.
True or false?
Yes, it is Boolean in this case. Okay. Of course, we can also define information in a non-Boolean, in intuitionist case, but we have not used.
Because in general, the internal logic of the topos is intuitionist.
Yes, absolutely. Here, in this application, absolutely, yes. But in this situation where we find the preceding result, that is for Shepard, here we use only Boolean, because it is just the topos of representation of a category. That is of a group.
Could I make a remark from a linguist? Okay, for complexity is a very important problem, I think, in linguistics. Semantic complexity is central in the problem. Now, this theory of Carnap and Bar-Hillel, I have applied it in the 70s in social linguistics to measure the complexity differences between different codes, social codes. So but it was applied in the simplest version as it was.
Here, in fact, we recompute this complexity using our construction of information spaces, okay, And we find interesting result for that. That in some sense, for example, the number of propositions in this language is of this size. Okay? It's very huge. Okay? 2 exponent n. But the only sentences or propositions which have a non-trivial information space are much less complex. That is, as soon as the sentence is very complex due to an excessive number of or of something which has nothing to do, the information vanishes. So you get point. And so it has 2 interesting consequences. First, you detect sentences which are in some sense the less complex, but the more informative. And also you say that they are exponentially less than the standard proposition. So it has something to do with complexity.
I had another remark on complexity in catastrophe theory, and if you have now semantic models of verbs, now and
of the world
of a language, and then you have the problem that you have in a sentence you have a verb and different nouns, or in the noun you have a kernel and an adjective, a noun and an adjective. And then you must compose this picture, this topological picture of one word, one letter of the verb, with the topological pictures of the other words into a kind of very complex space. And I don't see any way until now topology has proposed something to use to solve this global problem, and then you must also show that the different pictures match, or if they are contradictory, or if they are coherent. So there's practically there's a huge field of problems opening there.
You are totally right that looking, for example, at language constructed like this one, but including, for example, verb, it's possible. But to have something realistic, we have to find rules which exclude at most every combination to have a realistic or efficient language. And but it's not impossible that this could be said also expressed through the topology of this information space. In fact, what we expect is that what replaces the simple group here is something much more elaborated, like a collection of groupoids or something like that, which authorize to make the operation that Cuglioli works on that from the point of view of enunciative topology. So you have natural operation that we hope to be able to include in the semantic. Sorry.
Can you speak again?